who may be interested in taking a piece of math and figuring out how do I build an actual real world application of this? Like how do I solve problems that a group of engineers or scientists or sometimes just real people face? In particular, as you'll see later on in the talk, this particular, I say paper, but it's really a series of papers, ends up quite focusing on how do we solve problems that lawyers have. And that's a very fun community to interact with. I'm not even joking. All right. Oh, of course, this is together with my collaborators Seth Fry, Jules Hedges, and Philip Zell. All right, what am I going to do in this talk? I'm going to give you some background. It'll probably feel like too much. To me, maybe it'll feel like too little. To Seth, it's definitely too little. But some background on institutions and governance, sort of the underlying sort of domain from which these problems are emerging. I'll do a very light intro to compositional game theory, and Fabrizio has already done that for you yesterday, so I don't want to waste too much time on it. And discuss more precisely how do we communicate it to a bunch of social scientists. So Fabrizio maybe talk about how it could be used in blockchain and crypto and make people money. Well, I don't think we're going to be making people money through these applications, but we hope at least to build maybe a slightly fairer, more equitable world. We'll go through a bunch of examples. I'm going to spend some time complaining about real-world applications. It's just, think of it as therapy for myself, because it's been so frustrating building for a bunch of real-world people and lawyers. And I want you kind of to experience some of my pain, but hopefully that will be, how do I say it, enlightening. And then remind me, because I didn't want to include it in the presentation because I always felt it was already getting too long, but hopefully to motivate some problems that you may not normally encounter in ACT, partly because the areas next to applied category 3 are very much math and computer science. So how do we, or at least the physical sciences. All right, let's start with a tasty little conjecture that was formulated by Elinor Ostrom. She's an institutional economist, one of the first female Nobel laureates, that there exists a set of shared and essential building blocks from which any governance system can be built. And here we're claiming that a governance system, whatever that is, consists of a set of persistent mechanism institutions that regulate the behavior of a set of agents. To give you a little bit more background on what governance is, well, there's not really any good definition out there, or there's a million definitions, all of which have no structure. So people kind of approach it by just like, what are some of the examples? So governance, in this sense, is often implied to be a form of control. So if you're on Facebook, for example, getting reported, and you do say something bad, getting reported is a form of governance. So the click, report, post to group admins. If you do something, if you keep doing it, you might get blocked. If you do really, really bad things, like post racist commentary, you might get a visit from the cops. This is from like 2015 from somebody's Facebook post. Of course, it's from Florida. No offense. So these kinds of Facebook posts, or this kind of governance, we usually call laws or rules. But governance is more than just laws. Oftentimes it looks like social norms, like we have social norms when we walk into a room and start talking to each other. It takes the form of markets, where you and I sort of trade along a price that restricts or constrains our ability to purchase things. And also sometimes looks like code and software. So 2 points here about governance is that governance, so writ small is about control, but governance writ large is about designing for collective action. So institutional governance system is a setting, a design for collective action. And that's kind of like the underlying text here. What we're really trying to do when we optimize or design these systems, we're trying to sort of build for a social system that can achieve a collective, some sort of collective result. And that designing governance system is really, really hard. Unfortunately, you can't quite just plug wires into each other. And I'll kind of like talk about why OpenGates in some sense fails to accomplish the goals of these design challenges. Partly the problem here is that people have to do it themselves, because designing governance systems is fundamentally a kind of political process. People contest with each other, argue, And it's truly deeply exhausting. It's an exhausting process that people really oftentimes don't have time for or don't want to get into. And this ties into this idea that, if we're building, tools, those tools should ideally be somehow accessible or part of this political process, as opposed to just, oh, here's a bunch of predictions from some experts, right? Because that's just not how these kinds of systems work and how they're deployed. All right, so what we kind of want to build, and sort of staying in our lane in some sense, we want to build kind of like CAD for governance. What is that? Lots of people means lots of different things, but roughly speaking, Seth, at least, who's our kind of resident institutionalist, likes to think about it in terms of a modeling tool for more integrated, multi-stage, hierarchical, and modularized kinds of mechanism in institutions. So, from the point of view of this community, it's very much about like, how do I stick things together in all sorts of different ways. So lots and lots and lots of people want something like CAD for governance. Leonid Hurwicz, one of the sort of founders of mechanism design, Elinor Ostrom, institutional economist. But you can find versions of this in law, international development, animal behavior. I have not read that citation, but I am told that it actually exists, and I find that hilarious. Sustainability science, there's a really sort of like fun paper where they're talking about trying to build ecological networks of governance. Anyways, this is very, very, very much a need in the social sciences, to a degree that's like, when I was, I guess, entering into the field, I found quite surprising in a way. So there are different candidates for this kind of CAD for governance that have already exist. So game theory is a candidate, but game theory wasn't really made for this. So game theory is mostly used for toy models, or even when you sort of focus on a particular real world thing, you're often focusing on like what I think is like, you don't think about the entire sort of like role of the executive in a firm. You just like, oh, this is the executive compensation package, right? And it features like 3 variables, and that's effectively your game theoretic model in most like actual cases. Most of this stuff has, for the longest time, been focused on pencil or paper. You don't really have rich descriptions, and basically you dumb down the world to be as simple as your model is, and definitely not improving or increasing the complexity of the model. A good way of thinking about this is that game theory is it's a tool designed for economists. But what if it was not for economists, and actually not for economics journals? Very important. So here's another alternative that's a little bit more, I suppose, our style. This is something called an action situation. It's a framework designed by an economist named Elinor Ostrom, which I mentioned earlier. I won't go too long to like what exactly this all means, but the key thing you want to sort of like observe about this is that this is about breaking up a relatively complicated social situation into modular chunks. There are actors, positions, benefits and costs, information, and then you can plug things into all these things. You can have boundary rules, position rules, information rules. And this is kind of like a formalism, lightweight formalism for thinking about complicated, complex social situations. It's good to understand like what this is actually used for, because it's kind of used for 2 different things, right? One, it's used as an ethnographic framework. You're like, you're a person, you go deep embedded into a community, you try to understand what the hell is going on, and you write down basically a bunch of natural language statements and organize those statements into this format. But you also sometimes use it, you give this stuff directly to the actors. So it's like easy enough for them to parse and use that they can actually use it, in a feasible manner to argue about and design their own institutions. So kind of a quick way of thinking about this is there is some sort of underneath the hood notion of interaction or networking between action situations. And really what they're doing is they're just sharing kind of institutional statements, just natural language statements. It's kind of like if you, it's not very anachronistic, not appropriate, but you could kind of imagine this is like the way you would use an LLM to interpret and sort of design these things, right? You're just like, oh, just feed a bunch of natural language text statements. You get something out at the end of the day. Hopefully it works. It's very different from the more formal game theoretic approach. So these are a couple candidates, game theory as it is now, action situations. And they all have different kinds of problems with them. So game theory, as I mentioned, another way of thinking about it is just there's exponential growth in game trees and matrices, too many equilibria in these complicated settings. It's just like, it's actually just not useful in some sense, trying to like focus on solution concepts. And we've had this like dark experience of like, what are we doing? Why are we calculating Nash equilibria for this? We're just like literally like throwing darts in the dark. Of course, the action situation, even though it's like good as a framework, it's really hard to implement computationally, at least it has been. And it's not really general enough to describe any cases. There are a bunch of other candidates. Carter did also kind of like a text-based approach. Lubel, I think I mentioned this earlier, has a more kind of network ecology approach. Natico, this is just literally just like, well, it's ABMs, but it uses this specific kind of like way of categorizing institutional statements. A little bit like a computational version of ethnography, if you want to think about it that way, just organizing a bunch of plain text. So, okay, lots of reasons that these things don't kind of fill the job of what we think of category governance. And of course, this is leading to things you kind of expect or know. So imagine if we had a game theory that was bad for proving things. That's not totally true, but bad for certain kinds of proving things. Not about solving solution concepts, not strictly numerical, which is usually thought of as a problem for economists, but was suited to these kinds of things, the things we care about when we talk about category governance. So finding structural commonalities used for prototyping, capturing systems of games. And of course, that's how we get to compositional game theory. So game theory, just to summarize again, this more mathematical version, theory of interacting rational agents, players make observations and then make choices, inputs and outputs kind of thing. The group choices of all the people, all the decisions, are what determine the ultimate payoffs. And then players act to maximize these payoffs. And in some sense, kind of the point here is that people's beliefs or agents' beliefs actually causally affect their the outcomes of these games, which is the key sort of like thing that's different about open games versus any other kind of process theoretic framework. And the global view of this is that you can sort of, once you have everything specified, you can compute various equilibria like Nash, Bayes Nash, etc. So open games is a new formal language for game theoretic reasoning. Technically, 2018 was kind of like the core paper, but people have been talking about it. I think Neil's been on this since like 2006. And also, very important, there's a software implementation for the game theoretic modeling. I just realized I can look at my screen. I don't actually look at them. All right, what's an open game? Those diagrams you feel very comfortable with. Building blocks, yeah, compose larger open games, some simpler open games. There's, different atomic building blocks. So they're like sort of decisions where players make single decisions about, they have some sort of like, basically just set of actions. And then there are computations, which can be just like functions. They just take an input, output, and output kind of deterministically without any sort of special consideration. And from these things, you can build up all the sort of open games you might want. And then there are a few kind of compositional operations, sequential and parallel. Parallel composition, similar product, and sequential composition, just the composition in the category of open games. What can you do with these things? You can produce things like prisoner's dilemmas. So in this case, what a simultaneous game played by player 1 and player 2. Y1 is the action P1, Y2 is action P2. They go to an outcome function or a utility function at the end, and then that returns a set of rewards that condition the behavior of the two players. So this is just the handy-dandy kind of like summary of the different operations. You guys should be fairly familiar with this already, but obviously you can substitute a game for a different game as long as the inputs and outputs match. There's a sequential and parallel composition operators that I mentioned. There's also a branching operator, which is essentially just a specific kind of game where I'm sort of like choosing between game A or game B, and then you play those games. Okay. Nicely, there's an open games engine written in Haskell, which allows you to build up models quickly, allows you to analyze models interactively. You can have automated tests running in the background to make sure you're actually like things are working, and that's sort of like certain, not necessarily like just like type checking, but actually making sure like some of these games are like good. And integrated with ML frameworks. This is a claim that I cannot verify since I've never used any of the ML features. But there's also a lot of missing features, and we'll go into some of those things later. So here's a fork. So this is a talk about applications, but obviously there's a lot of math kind of going on underneath the hood. So obviously there's the original paper, Ghani. There's kind of lens theoretic representation of this that Jules actually likes to use natively. There's Bayes Nash by Jeff Bolt. Oh God, I can't. Anyways, from 2019, extending this this framework to Bayesian games. There's a relationship to learning that was developed in actually I think one of the first ACT conferences, and then there's some stuff on graphs by Elena and others here. So, but we're going to be focused on the applications, which is, so we're going to be working with this engine and asking how do we represent games in this engine? How do we analyze games in this engine? And what can you do with all this? What's the kind of like the upshot? What does this solve for an actual problem domain? So some benefits of the engine, just to summarize, yeah, you get compositionality, clearly. Nice thing is there's a, what we call, there's a very nice relationship between the model and the code. The code actually just looks exactly like the way you would kind of specify an actual open game on pen and paper. You can approach this, this allows you to kind of approach the model in a, well, not only the model, but the code in kind of this divide and conquer fashion. You can do things with the code like, you know, save it and then call it and substitute it in other code. And it was kind of magical when we first started doing this. And it actually worked. We were like, all breathe a huge sigh of relief that this complicated engine that we hadn't really tested substitution for somehow did actually work. So that was fabulous. And you can also modularize your code and maintain a proper game theoretic meaning. So this is what the code actually looks like. You have the inputs X, the outputs Y. So inputs X would be observations, Y would be actions. And then you have the feedback R, that is, you know, like a set of agents in the game, might be sort of like need to evaluate, and then the game sort of returns a set of additional utility signals to games further down the downstream. And for the Prisoner's Dilemma open game, this is exactly what that looked like. And I think Fabrizio literally used the same slide from Philip. Okay, so let's get to some meat for building actual institutions. So this is one of the first, I should say, semi-realistic examples. There's, if you actually wanted to model a carbon credit market, you would get much more complicated. But this kind of gives you a quick sense of some of the complexity of things that are going on. So I have a bunch of carbon credit permits, effectively, basically saying, hey, this is how much you can pollute. That is allocated to a number of firms. So we just assume there's some initial allocation, right? And then there's kind of like in some sense, kind of a, well, okay, so the firms then produce using their allocations. Then some firms may produce more than they should have. So they need to buy more carbon credits. Some firms produce less, so they can resell these things. It's the way the market is designed. So there's basically a resale stage where the firms are then go into this kind of market. They enter the sale game, and then that ultimately goes into a second round of production, right? So this is like really sort of like just, essentially we built this because it is an actual real game, modeling carbon credits at a relatively high level of abstraction, but it kind of illustrates the kind of the compositional, parallel, kind of different things put together in a way that, let's say, economists are familiar with. But remember, we're not really trying to sell this to economists. In fact, the basic argument of the paper is, yeah, compositional game theory is not useful to economists in the sense of academic economists who write papers and care about things like solution concepts. Compositional game theory is, maybe, we think, actually, we're pretty sure, it is useful to social scientists in the sense that we have social scientists actually using it. So you apply software engineering to social designs, and it leads to easier prototyping, as I've already said, and giving you a taste of the million citations of social scientists asking for something like this. So here's an actual example from, that's really quite fun, from the actual, let's say, institutional social science literature. So this is specifically from Ostrom, 1990, as well as Shivakoti and Ostrom, 2002. Basically, they, these are people who actually go into the fields and like try to understand what communities are actually doing. And they went to Nepal and sort of observed that in many cases, there's this situation where I might have a source of water. It's an irrigation canal, maybe it's like a small creek or river. And then, there are plots owned by different farmers built on sort of the side of this canal, right? And of course, you're doing farming. Kind of fun fact, this entire sort of project started on analysis of like farm contracts, and I won't go into that, but so I have a bunch of farms and they're all sitting on the side of the canal. And of course, the water is it's a common pool resource. It's shared, it's scarce. And how do you adjudicate and govern this resource? So farmers, especially the ones further ahead, have this asymmetry. Or farmers, because of this, the fact that they're looking at different positions, the ones ahead have this distinct advantage because they can just like consume as much water as they want. But if they keep doing that, then the farmers at the end don't get any water and they have problems. So there are various different kinds of solutions to this. Ostrom's point, which I'll go into too far, is that people, when they are faced with these situations, they can come up with their own solutions that are actually much better than if I'm going to privatize everything here, and you just pay for, because one is more valuable, you just pay more for one, or you have a central authority called maybe the government that comes and says, I'm going to look at you all and make sure you're following the rules. Is that people can come up with interesting kinds of solutions that actually work much better in practice, and this is actually in fact the observed outcome in most of these settings. So in this case, and I'll mention an important part of this game is that there are monitors who look at these games and basically make sure people aren't over-consuming water, right? In fact, there's many ways you can design this setup. So there's there's no controls. You just exploit how you like. You can have unpaid third-party monitor for obvious reasons. That's gonna, may be problematic because monitoring things does have a cost, right? Who wants to pay that cost if you can shirk? So you kind of have a fixed pay. You can pay from sort of penalties, so you're incentivized to fine shirking. You can pay in percentage of yield. That is yield from the farm. We're going to cover a bunch of these things and this idea of a rotating monitor, where you have different sort of seasons. You have a different member of the sort of owner of one of the plots being the monitor. So basic system. I'm not going to try to explain. Go ahead. Yeah.
Farmers just pay for the amount of water.
So yeah, the question is one of these options just each farmer pays for the amount of water they use, right? It is not mentioned here, but you probably could. I mean, the issue with that is you still need effectively a monitor, maybe a technical monitor that actually measures this is the amount of water that's consumed. There's very little infrastructure in these cases, so it's usually a person checking. So I have a basic system. So I have a bunch of farmers. Let's say farmer 3 is, way down on the end of the road. Farmer 1 is at the top. And farmer 1 is going to tend to get, the best outcomes no matter what, right? But if it, where is it? you can see that, I think it was like 862, actually, effectively what this should be telling you is that if a farmer one floods, as in uses as much as they like, they got obviously an optimal benefit. But if they don't, and everybody chooses to crack, so just like get a little bit of water, that is socially optimal. So everybody gets something, and the production of the entire sort of set of farms is optimized. If you add in an external monitor, so it just directly changes. So you just add an external monitor as a third player. They enforce a penalty on the farmers, and that penalty is just realized as a kind of like across the board. It's just like a direct sort of transformation of those matrices. And then if you have a rotating monitor, so in this case, okay, I have some sort of random number generator that selects, sometimes it's going to be farmer one, sometimes it's going to be farmer two, sometimes it's going to be farmer three. Each one of these farmers is going to change based on, if they also are the monitor, they can work and crack, work and flood, shirk and crack, shirk and flood. Ultimately, what this kind of points down to is it's not really clear, like what are the equilibria here? But the point is, like, overall, this is actually this is the setting that you see most often, that like in practice, like observed in different canals, and this is like mostly in Nepal, and this is in some sense like the empirically optimal position.
These are things.
Yes, these numbers are things we just put in. Yeah.
From your simulation.
Yes. Yeah.
They're parameters in this.
Right. So like 851 should be the payoff to farmer one, the payoff to farmer two, and the payoff to farmer three. Under this case, it's very hard to read, but this would be like farmer three decides to flood, farmer two decides to work, so they're actually monitoring, but they're cracking, so they're just consuming what they're supposed to, and farmer one is also cracking. So in this case, farmer three, the one at the end of the thing, is just trying to use as much as possible, which is obviously they're very heavily constrained, because if they flood, it doesn't really matter, right? So when you convert this to open games, this is kind of what it looks like. It's kind of like a fun part of this is when we built this. Just make sure we're doing okay. Okay, I should probably hurry up. When we actually represent this, it actually looks like the canal. It's kind of like a fun little side feature of this. But you have per plot, you have a farmer decision, and then you have a bunch of decision factors, which I can represent here, that sort of play into that particular farmer's decision. So each plot then, so there's a kind of input of, so literally just like a kind of like a value, like you could say the total amount of water in literally like liters or something, going in from this reservoir into plots. They consume this. Farmer one makes a choice, plays in plot one, farmer two, farmer three, and then there's just remaining water. So this represents what do we think of as the unconstrained, it's like everybody does what they want situation. In diagram C, you have this case where, okay, I just have an external monitor. It's not farmer one, farmer two, or farmer three. And then, the monitor has some earnings, which are sometimes tied to the plots. And then there's a choice of the monitor's effort. And then do they actually just take the money, or do they actually do the work? And then there's remaining water at the end. And finally, in this rotating set, these farmers go in this random draw, and then there's a monitor effort. And in this case, I'll note the presence of a barren plot here, because the idea is that this is often tied to a setting where these farmers, whoever gets the random draw, is incentivized not only to, they're incentivized to do the monitoring because they're given access to a plot at the end of the canal that they can only use, and is only productive if it is actually, if they actually do the work. right? So they're directly incentivized. So you can see like there's all sorts of like fun little ways to configure incentives in a way that is like very, very, that's, how do I say it, more respective of the real world, where you can like build little things. You can take advantage of net features of the world, like the fact that, water runs downstream, right? And it's very hard to represent these in this world, right? How the hell do you interpret these giant tensors, basically? Okay, little side plot into policymaking and branching. So this is basically a game, another example that's sourced directly from Hurwicz. The idea here is I'm basically a policymaker or decision maker who needs to decide whether I'm going to be, how do I say it? So I usually think of this in terms of like farms. Anyways, I'm not gonna go. So imagine like, there's like a regime where I'm like a workers and a landlord, or workers and like on a piece of property, like a farm, have a share of the income from that farm, right? Alternately, you can imagine just like there's a landlord, they get the proceeds and they pay the workers a wage, right? Of course, this is a very, very, very common sort of setting in which I need to make a decision based on the outputs and the effort and maybe sometimes the equitable distribution. As a decision maker, like, should I sort of implement the share thing or should I implement this wage thing? And sometimes it's the workers and the landlords negotiating between themselves, right? So they're not only the actors in these different games, they are also the decision makers to choose between games. And open games have this nice feature where I have this branching operator to choose between these two things. Some learnings from some of this work. You need a model of agents and roles before you get off the ground. This comes, the reason we mention this is that game theory doesn't actually come naturally with a definition. It's kind of like abstracts over the fact that this is the agent with a name that might have like multiple decisions. So being able to define these agents and roles is something like pre-game theoretic, and thus pre-compositional game theoretic and it's very, very important for thinking about and actually applying these things in practice. Compositional game theory is also really terrible at certain things like helping you design payoffs. It just doesn't do anything there. It's kind of orthogonal to that whole effort of how exactly we sort of design these payoff functions, these numbers at the end of the day that go into these calculations, which is, we're thinking about like, the fact that we have this nice compositional structure maybe actually allows us to plug into different ways of shipping these parameters, inferring these parameters. So maybe that's an advantage. Equilibrium checking is very useful in general, but it's really, really far from actually being able to optimize these complicated, really, really, really complicated kinds of institutions. So there's, it's nice to have, but it's not really maybe the most useful thing. It is really useful to do a lot of rapid prototyping, but that said, I think actually that has improved a lot in the past 2 years since we really wrote this paper. But the point is the potential is there. And I also mentioned, substitution actually works in practice, which is like, was really nice. It sounds like really trivial, but it was nice that it actually just worked. All right, a brief interlude. I might skip over this really quickly. So it was interesting to me as I was doing this, because I've kind of been part of observing applied category theory for a while. This is like kind of an evolution, or there's different variations of kinds of applied category that we see in practice in this community, right? And that open games, circa 2023, it's kind of like evolved from different parts of this, the sort of compositional game theory. Now we're finally up to the level of like building engineering tools that engineers and practitioners actually use. And it's interesting to think about, to what degree open games, as we've kind of like, as it's evolved from 2018, which is when I guess it was first really, well, not developed, but published at least, has responded to different problems of applied category theory that were noted in ACT number 1. So this is a workshop we had when we discussed like, oh, here are all the limitations for actually applying category theory. Unfortunately, I think I literally don't have enough time to go over all of this, but a couple of things. One, we took to heart this lesson that category the thing at the bottom, that category theorists think that category theory is super cool and just want to communicate these results directly to scientists, but that's a catastrophic mistake. It just turns people away, confuses things, and we, at least in this case, or maybe like not scientists, engineers, certain kinds of practitioners, but in this case, we very much tried, and you'll see kind of in the next few examples, to kind of de-emphasize the category theory, emphasize the connection to modularity, compositionality, and organized under this sort of pitch around software engineering. We've also, I think, at least speaking from the perspective of compositional games, we've done decently well on some of the other things. We still don't interact with data very well, but maybe Fabrizio and his team will be improving that in the coming years. All right. Next set of examples. So this is a different paper, but it kind of builds on the institutional engineering part. This really focused on legal contracts and software engineering. So first off, it's once again emphasizing that that compositional game theory, we're selling it as a kind of engineering. So what does that mean? It means we permit modularity, reuse, abstraction in game design. It's really directly analogous to how modern software is built by connecting standard components, functions, classes, modules. And that sort of the argument is that compositional game theory is great because it allows us to build these kinds of modern software languages. In fact, we take that all the way through and literally just direct, this is like a literal illustration of that. In between, there's this thing called compositional game theory. But really we just say, okay, there's contract drafting. So this is the practice of how do we draft contracts as lawyers? And then we try to say, what is the sort of thing that this thing corresponds to in software engineering? And the pitch is, if you want contract drafting to look like software engineering, you should be using this set of software libraries that we built using category theory. Oh, sorry, I don't know how that got copied. So this is a set of work that was done on an actual data set. It's not the usual kind of data set you might imagine. It is actually a bunch of contracts. The contracts are actually nicely enriched with certain kinds of metadata. So this is an example from a sale of goods contract. And this is an example from a clause library / contract drafting startup called LawGood. They basically just present normal contracts, but you have this nice little feature where you can go to these particular clauses. You can say, basically, I'm going to change the clause. So instead of getting delivered to the shipper's location, so basically not getting it delivered, you can have it delivered to the purchaser's location. Or if you're doing packaging shipping, you can do like a neutral thing where, like the benefits both the seller and the purchaser, but you can have like various different clauses that have different sort of locations on this good for which party. Of course, what should this remind you of is the fact these are effectively either kind of like different games. Each clause is effectively a different game that you might want to plug into a much larger game called the entire sort of the game that models the entire contract. What's also additionally nice is that there's additional data on like what people prefer, whether the purchasers or sellers. So it kind of gives you a nice sort of at least ordinal description of what the preferences are and what the kind of not the preferences, but the preferences and kind of like utility. This is the full list. When you actually build an entire model of the entire sale of goods contract, these are all the different clauses. So we're clause categories. And then there's a bunch of clause options, favorable to purchaser, neutral, etc. You can see like how just like looking at this, it becomes quite a mess to model. If you want to model a full contract and actually understand the space around that contract, you have to model all of these things. And remember, this is literally just like, I'm going to buy, a washing machine from you, right? You have to deliver it to me. It's literally something that simple, but it's already this complicated. Can you imagine a bunch of economists doing anything with game theory on that? No, the answer is no. The answer is nothing like this even exists in any like law and economics journal. So just give you an example of, so we actually like built diagrams and models for each one of these clauses. So this would be inspection. So how does this work? So okay. So I have maybe 10 days. I get the shipment. I have 10 days to actually decide, is this conformant? So I need to decide, okay, do I say this is conformant or not? But the thing is, that imposes a cost on the seller and a cost also on myself as the buyer. Obviously, if it's non-conformant and it is, then I'm suffering some sort of damage. But when you look at the sort of the complicated, these are the different things I need to go into, how do I say it? Basically, this is what this is showing is a more complicated version of the inspection decision, where the seller has designed this contract to make it fussier for the buyer to actually report non-conformation, right? So there's it's just imposing different kinds of additional costs and sort of conditions on the buyer so that they will hopefully report less. And this is requires a different game that needs to go into that inspection decision box there. This is, I'm not going to repeat this, but this is the favorable to purchaser one. You'll notice it's, of course, simpler. And then this is the clause that we had to read and interpret for favorable to seller. So literally converting this into a diagram. It is not easy. And I kind of want to illustrate this because you don't get to magically just remove the complexity of the world with open games. You still need to deal with it somehow. The point is, this is one paragraph, one clause option in a much longer contract. And this gives us a kind of a reasonable way, software engineering projects are complicated. You can't get away with that. But at least you have all these tools like modularity and abstraction to reuse different pieces. And this is effectively that approach. This is another example. This would be the limited liability representation. I'm actually running out of time, so I'm going to just go on. At the end of the day, what this allows you to do is explore kind of the contract space. This is a very sort of hand-done sort of model on two very specific sort of subclauses where we're just combining liability with these different subcontracting clauses. But the point is, it allows you to explore going from the left to right, from simple to complicated. So I have multiple sort of clauses get stuck together, and then you can use that to evaluate, are these contracts more biased, generally speaking, or are they more fair? And those come with actual numbers and parameters that get spit out and back that data at the end of the day. We also sort of actually went through the process, worked with a lawyer to figure out where would this actually, reasonably be built into an application? Where would actual lawyers see any of this? And the upshot of this diagram / exploration, which I learned truly a lot about contract drafting in this process, but that the most likely places that compositional game theory, and this may apply if you are thinking about building such applications and tools and using your own applications, is that they're most likely to kind of be useful on top of existing kinds of software that are already being used inside some sort of business or technical process. So in this case, being built directly on top of clause libraries like LawGood that I showed you earlier. You can imagine it built on automatic contract review things like LexCheck, as well as sort of post-signing analytics type things. So there's different use cases for this generic technology, but mostly they're going to be built, most likely at least, built on top of existing tooling support. All right, and last little piece on smart contracts. So we took this even further in search of actual applications. So we decided, okay, we have this model for simple contracts. What if we did it for an actual contract that a lot of people use, and it's actually kind of important for things like the US economy? So there's this thing called the Y Combinator safe. How many people heard of this thing before? No? Okay, a few? Yeah? Okay. So what this is, it stands for Simple Agreement for Future Equity. Y Combinator is a well-known startup incubator. It's basically used by a large number, truly large number of startups to raise funds without actually saying this is a share. So it's basically this truly the dumbest version, to say, I'm going to give you money, and you, in return, when you do have shares and this complicated technical arrangement, I'm going to give you not tokens, but some sort of equity. I'm going to give you shares in that sort of share model. Because people, when you're just doing a startup, you don't want to define this really, really complicated game that people need to play around shares and who owns this much and what the allocations are. You just want to say, I want money. Please give it to me. I'll give you something in return, right? And a safe allows you to do that quickly and relatively safely. Okay. This is the actual game that we built to model the entire safe. I should say this, I have issues with this, and this is very much ongoing work in some sense. Because actually there's like huge chunks of the contract that are not actually modeled. We didn't go through the entire sort of like super rigorous clause by clause model for this, because there are things like regarding jurisdictions that actually like should be like dangling wires there. But essentially this is saying like, hey, I'm gonna sign a safe agreement here. That's, okay. It's okay, I'll get it. So roughly speaking, there are, okay, maybe not. Wait, how does that work? All right, you just have to trust me and say that, so this is the signature of the safe agreement. There's this calculation part over here where they're basically deciding right before basically the Series A, when there's basically an allocation of equity to all the different investors, they basically need to make a decision about like, okay, they have this decision where they can decide to basically exit at that point and exit at the sort of share price at the Series A, or they can decide to stick around and basically continue playing the game. There's more Series B, Series Cs, and things that get exited. So basically, this is like the chief decision that's actually defined in the YC safe is this issue of like, okay, I'm gonna own certain things. Obviously, there's questions around like, how long is this thing gonna last? To what fundraising round? But then the key thing that actually defines utility is their kind of exit point from the setting, right? Which is interesting if you think about it, because we don't usually think about, if you're building a startup, like, oh, I'm about building value in this company. But from your investor's perspective, actually, it's all about that exit. That's the only action and decision they get to make in this entire institutional thing, this particular design. And it's interesting because there are variations of the safe, which I'm not showing here, that allow you to, have more optionality in decision making in some sense. But of course, they're more complicated. So why do we do this model? There is, different reasons, but in this case, we actually wanted to build a version of the safe for these blockchain-based organizations called DAOs. DAOs don't really have because they're not legal entities, they can't like easily sign legal contracts. And the idea is we could build a strategically equivalent in a formal sense, because we have a formal model of the safe, using this game. We can build a formal smart contract that actually just directly executes that safe as a smart contract. So it's actually been built, though it's not been deployed. A lot of bugs still in this. And this is something that actually the Web3 community is actually quite interested in some versions of this. And I'll just conclude, and we'll have like a few minutes for questions. So finally, just to sum up, compositional game theory, what does it do? It brings modularity use and abstraction to game theory, i.e. things that we care about from a software engineering perspective. Increases the parsimony of game representations from traditional game theory, which is really nice for prototyping. Allows structural comparison, accelerates search and design, basically prototyping, and helps theorists in the sense of like social scientists, express real-world institutional complexity in a well-defined way. All right, with that, I just want to thank my collaborators, Jules, Philip, and Seth, who were with me on the first paper. Philip and Megan, we worked on the second paper on Clause the Games. And then Philip and Lance and I worked on the last example on the modeling of the Y Combinator safe. And Lance especially did the vast majority of the work in shipping the code. And with that, Thank you very much.
We've got 4 or 5 minutes for questions.
Thanks for this very interesting talk here. So you mentioned at some point at the beginning that one of the difficulties is with governance is that the players also design the game structure in a way that's up for contest. Do you have a way for to model a game that sort of, because the game, it looks like the game structure here is fixed in all these examples, right? It's built by the modeler. Can it vary in the game?
Yeah. So this is effectively what the branching operator is trying to do, but effectively, I mean, this doesn't nearly anywhere close to capture the actual imaginative, openness effectively of that, like when a bunch of people with really sharp interests, right, competing interests, go into a room and try to decide how I'm going to make decisions where this is the game that we're going to agree to play. There's no way you can capture that beforehand, right? At best, you can sort of articulate, oh, these are some like the outputs and the inputs. And then you kind of help them design this. So, which kind of revolves around, gets into like the rigidity of some of these tools that we're building, because they are still quite technical. They're not things that can evolve at the speed of text, let's say. Even like text is actually in some sense, like a problematic medium for making these kinds of arguments, right? People disagree, miscommunicate all the time. So it's just a really hard problem. But I think the idea is that you build this as kind of decision support mechanisms to help clarify, like if you're doing like giant like mergers and acquisitions thing, where it's like $1 billion, these parties are arguing through these formal processes. Like this is where something like this can like operate and be actually like potentially really useful.
When I look at Ostrom, she dealt with common good resources, and it's a very important distinction between common good resources and other. Number two, what she did, she combined game theoretic experiments and empirical data to arrive at a grammar for a variety of institutional structures.
Yes.
And that's a very engineeristic approach to economics. But the way you are approaching, you're already imposing a certain game theoretic notion uniformly. And in some of her experiments, the game theoretic predictions did not work. And that is why generation of the rules themselves became an important component of this. I just wanted to clarify the distinction between the way you're using Ostrom and in the way she arrived at some of her results. Thank you for the talk.
Well, quick responses, I agree. Yeah, there's a very much, kind of like the emphasis here is that solution concepts are not particularly useful in like most of the cases, because, well, they give bad predictions based on like, because you need to put in a bunch of parameters, like these parameter values, and obviously it's very sensitive to what the outcome, these numbers that you assign at the end of the day, right? So oftentimes it's a nice tool, but it's not something you should be depending on.
Okay, I think we should stop there. So thanks again, Josh. In this room, we have